Okay, so this is page 42, lesson 16, last lesson of the packet, the mean value theorem. Okay, so here's the mean value theorem. I'll talk about this in a moment, but first let's look at the intermediate value theorem, which we already know. And so basically, here's a picture of how the intermediate value theorem would apply on a graph. And with tables, you've got like, this is like the original, from the original table. And then the IVT is going to allow you to conclude that there is a time t between the endpoints on the interval that has a certain value. Okay, now in order to use the IVT, you have to have these three conditions, and then this is what you can conclude. Okay, so we've been doing that, so I won't talk about it more. The MVT says this. Okay, so first let me like read this, and then I'll look at it in the picture. Okay, so the mean value theorem says this. If f is continuous on the closed interval AB, so that includes A and B, and is differentiable on the open interval AB, so doesn't include, this interval does not include A and B. So f does not need to be differentiable at the endpoints. All right, differentiable means the derivative exists, so it doesn't need to exist at the endpoints. And then number 3, you find the slope of the secant line on the interval, which is this, which is this. Okay, so these are just 3 things that are always like representing the same thing. All right, so we're going to find that number. And then if we have these things, then we can conclude by the mean value theorem that there is a time t between A and B at which the derivative is equal to the slope of the secant line. All right, so let's look at the picture real quick, and then we'll jump into some examples. All right, so the picture is here. We've got f. Okay, the graph of f is continuous and differentiable. All right, differentiable, so there's no like points of discontinuity, which we already know because it's continuous, but then there's also no sharp corners. The derivative does not exist at a sharp corner. All right, so we've got this function f. The slope of this line is m secant. All right, that's the secant line. And what the MVT says is as long as you've got these 3 conditions met, continuity, differentiability, then there's got to exist this t somewhere between A and B, at which, if you look at that t value and you go to the graph, the tangent line at this t value is parallel to the secant line. Tangent line parallel to secant line. So what you end up with here is that this, which represents m tangent, is equal to m secant. Okay, so now let's actually jump into some problems. Guys, this might be a long video. If you're losing focus and you have to stop, just like mark the time that you stopped at and then go back to it when you feel like you could focus better. So you are given that f of t is a differentiable function. Selected values of f of t are shown in the table below, okay, right here. Guys, we're only going to do B. All right, well, just to save time, we won't do A, but we will do B. Okay, so first, guys, if they're telling you that a function is differentiable, let's say the other things that we can conclude. Okay, if a function is differentiable, some things you can conclude are that it is also continuous. So f of t is continuous. And then, guys, being differentiable not only means the original function is continuous, but it would mean that f prime of t is continuous, okay, if we needed it, if we needed to use it. So we have that information there. Okay, now guys, just to save some room, or not save room necessarily, but all right, never mind. I guess I won't do that. All right, I was going to write this little table over, but I don't think I need to do that. All right, so let me do like a little arrow, and then I'm going to expand this table. So I'm going to have T, and then there will be 3 columns. T in the middle, 3, 7. Okay. Now, what's in this table is going to be what we're trying to prove, okay? So this is not also going to be a F table. This is going to be an F prime table. So here I will put F prime of T. We don't know anything about F prime at the endpoints. But what we want to be happening here is we want to be able to say that that value exists in the derivative table. All right, so this is, wait, oh yeah, okay. And guys, by the way, let me write down here. So if you're asked to prove that the derivative is a value, but you're starting with like the original, like at the beginning of the derivative sequence, that's how you know it is the MVT that you're going to use versus the IVT. Okay, so let me mark the conditions that we need. Okay, so, all right, the first 2 conditions, actually, we could just write here. So number 1, this original has to be continuous, and number 2, it has to be differentiable, okay? This is pertaining to that there. And then guys, so that's 1, 2. The third condition is that this number here, all right, this is the third condition, is that that is equal to delta y over, in this case, delta t. That would be the third condition. If those 3 conditions are established, then, looking for a different color, okay, then what the MVT allows you to conclude is therefore this particular t exists. Okay, so now let's write this down. So our first 2 conditions are going to be this. But guys, they did not tell us f of t was continuous. So we have to set that up first because they didn't give it to us outright. So if they didn't give you something you need outright, we're just going to say like, you know, since this was given, and here's the things that we could conclude, this is the conclusion we want to make, that it's also continuous. So since f of t is, and you could just say DFF for differentiable, since f of t is differentiable, it is also continuous. And then you could use a transition word like so or thus. I'll just jump right into the 3 conditions. Okay, so we could say 1. F of t is continuous on 3 to 7. F of t is differentiable on the open interval 3 to 7. And guys, a good way of maybe remembering that this is a closed interval, this is an open one, is that if you look at our derivative table, I just put slashes under the endpoints, so it doesn't matter. Differentiability at the endpoints, the derivative existing at the endpoints does not matter. That's why these are soft parentheses. All right, now for the third condition, let me just say this. Let me say m secant equals delta y over delta t, and that is equal to, oh, let's verify. Guys, I forgot I have to verify this. Okay, so that would be delta t, all right, and that's 4. This is delta y, and that's 7. Okay, yeah, so I should definitely show that. So 7 over 4, in fact, does equal that. equals 7 over 4. Okay, so I'm just verifying that. And then, therefore, by the MVT, there is a T, and now we're going to tell our reader where it is located. There is a T, 3 is less than T is less than 7, at which f prime of T equals 7/4. Okay, so that's how you do that. Now for number 2, we will do part A. You are given that g of t is a twice differentiable function. Selected values of g prime of t are shown in the table below. Okay, so right here. Explain why there must be a time at which g prime of t equals 10. All right, guys, so this is how you can tell IVT or MVT. You look at the table you're given, g prime. Are you asked to explain something about g prime or g double prime? G prime. So if this thing that you're explaining about is the same as what you started with, then that is the IVT. Okay, so we're going to use IVT. So let me set up a new table. And the IVT expanded table it's the same as that. All right, this up here was the derivative. That's why it was MVT. So g prime of t, all right, I've got, I'm going to have this t in the middle, 0, 5, and the t I want is 10. Okay, so let's set up our conditions. Okay, so for IVT, first you need this to be continuous. All right, second, those y values cannot be equal. All right, now I'll put in these little inequality signs, and maybe I'll just like lightly circle that. That is the third condition. And then after we have these 3 conditions, now I'll circle this. We're going to be able to conclude, therefore, this t exists. Okay. So now this is going to be my first thing that I got to say. And they did not tell me this. Okay, they didn't say this was continuous. What they did was they said that g of t is a twice differentiable function. Okay, what does it mean that g of t is a twice differentiable function? What this means, maybe I'll just like write it over here. It means a few things. It means that g of t is differentiable. Okay, that's got to be clear. If it's twice differentiable, it's differentiable. But then it also means that g prime of t is differentiable, okay, because it's twice differentiable. And then, but what else can you say? Oh, you could say g of t continuous. And is there anything else you could say? Yes, g prime of t is continuous. And guys, it's actually this. It's actually that result that is going to be our first condition there. Okay, nice. But I have to establish it because they didn't like say it outright. So I'm just going to say this. Since g of t is twice differentiable, g prime of t is continuous. Okay, now we can launch into our 3 things. So 1, 2, 3. So 1, g prime of t is continuous on 0 to 5. Okay, g prime of 0 equals 3, and that is not equal to g prime of 5, which is 18. Okay, so 1, 2. Now 3 is this one. 3 is less than 10 is less than 18. Okay, so I have all of those. So therefore, by the IVT, there is a time t. 0 is less than t is less than 5, at which g prime of t equals 10. All right, guys, you know what? Okay, this is kind of long, so let me just pause here. And then in the next video, so this will be part 1, part 2 is going to be very similar, except there's going to be more values in the table. So we're going to have to choose a subinterval to work with. So we'll make that be part 2.